that took us a while, but we got the answer nonetheless. The second approach however deals with the fact that we can work with equations. We know that I equals V over R and P equals IV. We can plug this in there and say P equals V over R times V, which equals V squared over R. Now, if we use this approach, we don't even have to find I. Again, notice we're making use of Ohm's law. Therefore, P equals 80 squared divided by 360, which is 17.77 watts. One step calculation, we got the answer compared to step 1. Okay, now let's do some analysis on this, which will lead us into our next problem. Our bulb was rated at 40 watts. We are delivering 17.77 watts given an 80 volt source. The question is, how does this look like physically? Well, let's use an analogy of a door. Suppose I push the door a little and then I push it harder. The difference is, if I push it a little, it's going to move a little. If I push it harder, it's going to move a longer distance. The same thing we can apply here. The higher the wattage, the brighter the bulb. So if you're just giving 17.77 watts, it'll be very less bright, if you want to qualify it that way. The question now is, if I can give total 40 watts, and my resistance is 360 ohms, what should be my V source be? Okay, now we're just working back. In other words, what we're doing is, I'm not satisfied with 80 volts. I need to give it more. The question is, how much more? To answer that question, let's go back to our drawing board and rewrite the equation for power, which we derived in approach 2. We said that power was V squared over R. Now let's solve for R. If you multiply both sides by R, we get V squared equals P times R. Therefore, V has to equal the square root of PR. Now if we plug in values, we get V equals the square root of 80, wrong number. V equals the square root of 40, which is the power, 40 watts, times 360 ohms. Okay, so this comes out to just about 120 volts. Now, keep in mind the units also work out. Let me quickly show you how the units work out. We're doing square root of watts. Watts is just volts squared over ohm times ohms. Ohms cancel. This is square root of V squared, which is just volts. As we've shown above, as we just showed, we need to supply the circuit with 120 volts so that we get maximum power. Therefore, we're supplying 40 volts more power. For maximum brightness. Now, this example might not seem interesting to you because this is something which we never do at home. However, let's say you were rewiring a basement and say you had an AC source of some sort. Let's say it was time dependent, and you had two bulbs connected in such a way. You would say, alright, this bulb has a resistance R1, this bulb has a resistance R2, the power is the same for both. What is the voltage that I need to send through them so that I get the maximum brightness? Now that is something we always do. One more thing you want to do is, let's say your voltage is constrained, which it usually is in our household systems, to 110 volts RMS. This is RMS, just means root mean squared. It's just the average of the time varying signal, but nothing to worry about. Let's just say it's 110 volts. Let's say our voltage is constrained to 110 volts. There's only so much power, so much current that can go through the circuit. The thing is, how much current can I have going through the circuit without tripping my breakers? That is one of the questions that electricians ask themselves all the time. And hey, Ohm's law to the rescue. This question, this phenomenon, this theory will very much help you in answering that question.